All right, welcome back to the course Electrical Systems in Agricultural and Biosystems Engineering. This is lecture number 2 of the course, and we're just continuing off from where we left in the previous lecture on electrical circuits and their elements. And what we're going to do this time is solve problems involving computations that are tackling those that we have previously discussed in the first lecture. So let's proceed with one of the problems. We will be doing problems basically on wire electrical circuitry. And we start off with one, the basics involving the voltage and current rule. And we solve something on resistance, and then eventually the circuits that involve the loop rule and the junction rule of the Kirchhoff's laws, and then the Ohm's law. Okay, so let's begin with this problem. We have a circuit where we have a starter connected to a 12-volt battery, and well, the starter behaves like a resistor, so it has a resistance of 0.1 ohm. So we compute for the current across this starter. Just try to solve using the device. Let me just share my other screen. Okay, so this is the screen. Okay, just to show you the problem. Okay, so we have the exact problem written out. Now let's start drawing the circuitry. So we have a symbol, the symbol for the starter, something like this. So and it's connected to a battery that's 12 volts. We assume it's a DC battery, so the given symbols. And the starter again is behaving like a resistor, so there's a 0.1 ohm resistance. So the flow of the current is like this. Now this is the given. We have to find the current in amperes. Okay, and the unit for current is amperes. So let's try to solve the problem. We just know that the voltage is equals I current times the resistance. So dividing this by R, we get the equation V over R equals I. Okay. Now we have I equals V over R, and simply we can plug in the values of 12 volts and 0.1 ohm, and we get, okay, well, when you divide a number by a decimal value of a fraction, you just move it the place of the decimal. Okay, so we get now a value of 12 or 120 amperes. Okay, so this is the final answer. Right, we have the next question. Okay, we have here a platinum resistance thermometer with a given resistance of 100 ohms. at a certain condition in a hot bath that is 0 degrees Celsius. And the thermometer is lowered to a hot bath and the resistance becomes 123.5 ohms. The question is, what is the temperature of the hot bath? Now, this is going to be a problem that's going to tackle the uh, the change in the resistance of um, um, materials, and we have the material as a platinum metal. So first and foremost, the very important information that we have that is a constant to this material is the coefficient of resistance, and it's given as shown. It's 0.039 over or per degree Celsius. Okay, so with that, that is eventually the alpha, and we know that we have already the formula given for this one. So let's try to write out um, the equations. Okay, so right now, what's this? So we have the problem as shown. Okay, now the given. Okay, we have the R, the base. Okay, the base resistance RR equals R sub R 100 degree 0.0 ohm, and then the temperature, that's going to be the T R, or the initial, it's 0 degrees Celsius. We are actually finding for the TS. Okay, now the RS is given also, so it's 123.5 ohms, and the alpha is 0.03 or 0.00392 over 4 per degree Celsius. You have to find what? You have to find the TS. Now we know that the problem is solvable using the equation RS equals it's RS equals R sub R times 1 plus alpha times delta T. So solving for delta T, okay, because that delta T is equals T sub S minus T sub R, whereby we know T sub R. So we have to solve for delta T first. But since we know that T sub R is, okay, since delta T equals T sub S minus T sub R, and T sub R equals 0 degrees Celsius, we have delta T equals T sub S. So we can simply put T sub S instead of delta T. So R sub S equals R sub R times 1 plus alpha times T sub S. And rearrange the equation so that we can solve for the T sub S. Right, so we do so by moving um, variables. So we have R sub S over R sub R equals 1 plus alpha times T sub S. And okay, so we have um, delta times T sub S equals uh, 1 minus, oh, sorry, it's going to be R sub S over R sub R minus 1. And we move uh, the alpha to the right. So it becomes R S over R sub R minus the quantity minus 1, all quantity times alpha. But we can still further simplify this so that we can solve simply for just these values without the 1. Okay, we can remove the 1 over here. So we simplify by making this equation minus R sub R sub R. Since this would just cancel if or this is just equivalent to that one. Okay, so we have the final equation given, and we can simply plug in the values. R sub S is 123. Okay, we further simplify this to PS equals RS minus R sub R over R sub R times alpha. Okay, so this is 123.5 degrees. Sorry, it's ohms. Okay, it's ohms. And we minus 100 ohms all over 0.003 0.0392392 per degree Celsius times 100 ohms. And solving, we get P sub S. This is 23.5 ohms over 100 ohms, and we can move the degree Celsius so that this is simply just a number. All right, so we get we cancel this. Okay, the ohms will cancel, so that eventually we just get the unit of degrees Celsius. So TS is, when you solve this, okay, 23.5 over, oh, sorry, it's going to be 0. Or it's going to be 23.5 over 0.392 degrees Celsius. And TS is equal to 60.0 degrees Celsius. That is the temperature of the hot bath. It's actually not, it's a hot bath, not boiling point. Okay. Now this is the basis for the use of metals to determine the temperature of something. It's calibrated. We have the mercury mercury used to determine the temperature, and it's based on the expansion of this and also on the electrical conductivity. So we use metals also to determine certain properties of other materials, of for use in what they call this in sensing. Okay. All right, so next question. We move over to question number 3 and share my screen again, my other screen. All right. So we have a given DC circuit, and we have two voltage sources shown, and we have to solve for the current flowing through the circuit and the voltage change from points A to B at SVAB. Okay. All right, so we have the DC circuit again. And what we're going to do here is first we have to draw the circuit because it's not given. Okay, it's not provided in my slide presentation. So let's redraw it. We have two voltage sources as shown. One that is 10 volts and another that is 4 volts. And based on the drawings, they have different direction, okay, of the flow of the current. Since we have positive sign over here and another positive sign over there. And this is 2 ohms, while this one is 4 ohms. Question is for us to first solve the current flowing through the circuit, and next is to determine the voltage change. And this is the difference between the voltage of points A and B as shown. Right, so this is given. Find A, the I. Well, we have only one circuit, so all of these elements will be experiencing the same current. We'll have to attach a convention to our direction. It would have to depend on when you're going to do this. You can do that or do the opposite. But essentially, when you cross a certain element, particularly if the sign is negative, so you have to ensure that the convention is made use of. Okay, so we have our solution. We start off polish for that one. Resistance. Right, again, we have the loop rule. So the voltage across all the elements will sum up to 0. And we have how many elements? 1, 2, 3, 4, and So we can start with the convention. Oh, sorry, I forgot to put the values of the voltages. This is 4 ohms, and this is 10. This is 10 ohms. So we have the convention as again. I have to take note that this is the positive convention. So we start now with the first element, that is the voltage source. We take the voltage as, apologies, I wrote the wrong units. It's V. So we have 10 volts plus 2 ohms. Okay, times this is the current again. V equals to IR. So we have the same I across all the elements. So it would only change with the resistor, therefore. Okay, so this is the resistor. So we have R times I. Oh, it's going to be a minus because it's easy resistor. So take note of the convention. Minus 4 volts again, because the positive sign is, or it's against the flow of the positive convention that we adopted. So minus again 6 ohms. This is 6 ohms. 6 ohms times I minus 4 ohms times I equals 0. Okay, so we group similar terms, and this becomes what? 6 volts minus, we just add the values for the resistors. Okay, the resistance, it's going to be 12 ohms I equals 0. And okay, we move that one term, the other side. So this becomes 6 volts equals 12 ohms I. And solving for I, we get 6 volts over 12 ohms, and I is equal to 0.5 amperes. This is the part A, right? Part B, we solve for VAB, and VAB is simply across this branch of the circuit. And it is going to be VAB equals positive 10 volts minus 0.5 A times 2 ohms. VAB is thus equal to 10 volts minus 1 volt. VAB equals 9 volts. If you use the other side of the circuit, it's going to be the same. Okay. Actually, we solved for the other side, right? I was referring to the other portion when I did the demonstration about it. So we can solve it similarly. VAB is thus same as that. We have -4 plus or minus 6 ohms times 0.5 A minus 4 ohms times 0.5 A, get minus 4 volts. Okay, volts minus 0. Oh, sorry, that's going to be 3 volts minus 2 volts. So VAB, since we're using the other side, it's going to be negative 9 volts, but this is going to be the same. Okay, we're referring to the opposite direction. Okay, so this is all right. Next question. The last question is, we have the same given circuit, but just in a different presentation or different setup of resistors and voltage source. And the voltages are given as V1 12 volts, V2 3 volts, R1 is 50 ohms, R2 is 200 ohms, and R3 is 100 ohms. Again, we're trying to solve for this voltage change between AB, so which is, I think it's not given. I have to identify the AB. Okay, so let's identify AB. I think the problem is wrong. Okay, so we just have to solve for the current through the circuit. Okay, we're being asked for the current across the circuit. Let me just see the problem. Yeah, we're just going to solve actually this current, but because we have different circuits. All right, let's move to our the device so that we can solve. All right, we have the problem shown and the diagram already drawn. So we have to solve for the current for what? We have two circuit branches. This is one, and this is another. So what we'll do is, okay, we no longer have to, we have to use the loop and junction rules over here because there's a junction over here and we have two loops, right? We use equation 5 as provided in lecture 1. We use equation 5 and we identify I1 over here, and then I2 and I3 over here, because there is a junction. Okay, we have or we can yeah, so this is correct. So we can make use of this one. Now I'll just change the notation so that it's simpler to check my answer. So we use equation 5 in junction A, and we have I1 equals I2 plus I3. And we make use of the loop rule. Okay. Let's have E1. This is again voltage 1. This is the voltage 2. This is representative of the EMF across the E1. So we E1 minus R1 times I1 minus R2 I2 minus E2. Sorry, I made a mistake. So this is I think I have to change this again. I wasn't able to change it a while ago. So that we have one loop over here. But we can make just use of I2 and I3 to we have just these two loops. Yeah, maybe we can do that. So I'm moving away from my solution. But so we can also make use of still this one. So we have this 12 minus 50 I1 minus 200 I2 minus 3. Let's forgo the units. Again, this is going to be equal to 0. The other loop is E1 minus R1 I1 minus R3 I3, and it's equal to 0. This one. So we have 12 minus 50 I1 minus 100 I3 equals 0. Okay, we now substitute the first equation into equations 2 and 3. So that we have 12 minus 50 by 3. I2 plus I3 minus 200 times I2 This is minus 3. Okay, minus 3. The other equation becomes 12 minus 50 times I2 plus I3 minus 100 I3 equals 0. Simplifying, okay, by terms, so it becomes 9 minus 50 I2 plus 200 is going to be 250 I2 plus, or minus, sorry, minus 50 I3 equals 0. The other is 12 minus 50 I2 minus 150 I3. We have two equations and two unknowns in I2 and I3. So you can easily compute for the terms. But there's another simplification to this, okay? You can multiply this by 3 so that we can easily cancel I3. Oh, no, sorry, negative 3. Okay, so 3 times 9 is 27. Plus 12 minus 27, sorry, plus this 750 I2. Okay, again, we add the 50, so this is going to be 700. Okay, I'm cutting short the solution, so you can recheck this later. And we have I2 as, okay, this is going to be 15 over 700 amperes. Okay, this is the final answer. This is I2. I3 is simply what? It's 12 times or minus 50 times 15 over 700 minus 150 times I3. We get I3. You can simplify this. This is actually 0.21 amperes. And this becomes 12 minus 50 over 70. This is 8 times 0.21 minus 150 I3. I3 is equal to 10.93 over 150. Or this is 0.073 amperes. I1 is now just simply I2 plus I3. It's equal to 0.21 plus 0.073 amperes. It's just sorry, 0.021. 0.021. 0.094 amperes. Okay, so that's the final answers. Let's proceed to the next problem. We have another set of resistors in a given circuit. And the circuit is quite interesting because we have a set of series and parallel resistors. in combination with each other, and the given, only one given voltage source, which is 12 volts. The R1, R2, R3, R4, R5, and are given 4 ohms, 3 ohms, 2 ohms, 6 ohms, and 12 ohms. Okay, let's solve it. Right. There's a technique to solve for this kind of problem. We can first, we can actually solve for the different loop, okay, using the different loop. But there's a simple or a more interesting solution by first, well, uh, combining these two parallel resistors, and then combine that with uh, the other, which is in series to that combined, and then we have another one in parallel to the whole of that previous combined, and then in series again. Okay, let's solve for it. Okay, we know that V4 and V5. Okay, this is V4 and this is V5. We know that V4 5 equals each other, right? And we have I4 5 as equals I4 and I5. I sorry. Oh, it's going to be plus, okay, plus I5. Given that I for 5 equals V for 5 over R for 5. Okay, and I4 equals V4 over R4, and I5 equals V5 over R5. We can say that V for 5 over R5, R for 5 equals V4 over R4. Sorry. And plus V5 over R5. Okay. And so since the V4, V5 and the V4, 5 are just the same, so we can say that V4, 5 over R4, 5 equals V4, 5 over R4 plus 1, or no, it's V4, 5 over R5, and we can multiply this by 1 over V4, 5 to remove the numerator. So we get 1 over R4, 5 equals 1 over R4 plus 1 over R5. Numerically, just the same. So to solve for your R4, 5 is we get R4, 5 equals R4, R5 over R4 plus R5. Okay, this is just this one. Numerically, they're the same. Okay. Yeah, it's just the same because we have it becoming 1 over R4, 5 over R4, R5, and then this is R5 plus R4. And we do the reversal of the units. Okay, here and there. Okay, so we can now solve for R45, and it is what, just R45 equals 6 ohms times 12 ohms over all over 12 ohms plus 6 ohms, and this is what, this is 72 ohms over 18 ohms, and we get 4 ohms. Okay, so R45. Now we can add that simply to get R345. We get R3 plus R45, which is just 2 ohms plus 4 ohms, and we get 6 ohms for our R345. Now for R2345, same with the first solution that we did. So it's going to be R2 times R345 over what, R345 plus R2, and we get and when values are plugged in, we get 3 ohms times 6 ohms over 6 ohms plus 3 ohms, and we get R2345 equals 18 ohms. Okay, square root of that, okay? Because we have to cancel the ohms and get the same value. 9 ohms, sorry, I 8. 9 ohms, and we get R2345 equals 2 ohms. Okay, now R12345 is simply the addition of R1 plus R2345. It's 4 ohms plus 2 ohms. We get what? We get 6 ohms. Right. Now to solve for the I total, okay, we get what? We use the equation V equals to IR, where R is 1, 2, 3, 4, 5. Okay, so I is V over R 1, 2, 3, 4, 5. And we get 12 volts, okay, the source, over 6 ohms. We get 2 amperes. Okay, that's the final answer. I equals 2 amperes. I'm sorry. All right, so we've tackled the problems involving various circuit elements and in our electrical circuits. Okay, so the total current here as flowing is through the battery is 2 amperes. It would be distributing because there are junctions, okay, happening all around, so it's going to distribute. Okay, next discussion would be on the power factor, okay, and the power that we derive from the electricity that is circulated in a certain electrical circuit. Again, this is Ian, and I will be seeing you in the next lecture.